first question is asking us to find other angles that are equal to x. With Euclidean, dealing with Euclidean, you need to remember that if you have a statement that has a reason, you need to write out your reasons. If you don't provide your reasons, you're not going to get a mark. So remember those reasons. One, we realize we're given that d1 is equal to d4. They're both equal to x. Another angle that is equal to d1 is h1. Remember, CE is a tangent. CE is a tangent, and DBH is a triangle. So when we look at this angle is equal to this angle because of the tan chord theorem. If we isolate these two, this angle is equal to this angle because of the tan chord theorem. So D1 is equal to H1 because of the tan chord theorem. Equal to x, so we have another x. An interesting thing again that we realize is that we're given that BH is equal to BD. This is given. And in a triangle where two sides are equal, then these two angles have to be equal. So H1 is equal to angle D2Y, angles opposite equal sides. So we have another one that is also equal to x. So far we have 1, 2, we need 2 more. Another one that we can do is this one. This angle can be equated to this. The same tan chord. We isolated CA is a tangent. The triangle, we have our triangle. This angle is equal to this angle. So H1 is equal to B3. Tan chord theorem. So we have another one, BD. So we have B2, we have H1, we have B3. Another one that we can also see is from here, this angle and this one. H2 is equal to D4. D4 also tan chord theorem, because if you actually look at it, this triangle and part of this tangent, this angle, as well as this one. So we have our 4. Another one that we could also fit in is this angle, D1. Because we already proven that D2 is equal to x, we can use also the tan chord theorem to prove that B1 is equal to D2 and have B1 as an extra angle that is equal to x. The next question is asking us to prove that BD is parallel to GH. This line is parallel to this one. Proving parallelism between lines is not as difficult. It's not as difficult. If you remember the fun between parallel lines, between parallel lines that are both intersected by the same line, we have corresponding angles, such as this one. We have co-interior angles, where this angle plus this angle is equal to 180. We also have alternating angles, this angle being equal to this angle. They hold true if these lines are parallel. We can also use them to prove parallelism between lines. So if we have two lines, which we didn't know are parallel and are intersected by the same line, and we find that either one of these three is correct, the alternation, the co-interior, or the corresponding angle is true, then we can say these lines are therefore parallel. We're going to use the same logic here. So when we look at these two, we have BD and HG, and they do have a line intersecting them, So we can use one of these, either corresponding, co-interior, or alternating angles. Let's try looking at alternating angles. From this, we do see that we have this angle, D2, which is X, being equal to this one. And that's what we H2, the angle H2 is equal to the angle D2. It has already been proven. And because these two angles are equal, then that means that HG should be parallel to BD. Therefore, that means BD is parallel to HG. Why? Because of alternating angles. In the final question, we're asked that we need to prove that angle G2 is equal to 180 degrees minus 2x. This angle is equal to 180 degrees minus 2x. Let's try to isolate this quadrilateral to make things clearer. So, we have to prove that G2 is equal to 180 minus 2 degrees. One way we can do this is by looking at this triangle, the BDH triangle. In the BDH triangle, we've already been told that D2 is equal to H1 is equal to X. We've already proven that, right? So when we try to find the sum of the angles of this triangle, we're going to say D2 plus H1 plus B2 is equal to 180. Sum of angles triangle. This is going to be X plus B2 is equal to 180 degrees. Make B2 the subject of the formula is going to be 180 degrees minus transpose these x all to the other side, 2x. So from this point we have B2 as 180 minus 2x. From this point, you can use a lot of different ways to go about proving that G2 is equal to 180 minus 2x, but the quickest way that we're going to use is the exterior angle of a cyclic quad. The theorem states that the exterior angle of a cyclic quad is equal to the interior opposite angle. So, it says G2 is equal to the two exterior angles of cyclic y. Therefore, G2 is equal to 180 minus 2x. There are different ways to go about this, but you still have to get, but you're still going to get 180 minus 2x.